after watching this video lecture, students will be able to understand the definition of buffers and how they work. They'll be able to calculate pH and pOH of buffered solutions using the ice table method or the Henderson-hasselbalch equation. And students will be able to calculate the pH and pOH of buffered solutions after acid or base has been added. So buffers are solutions that resist change to pH when you add strong acids or strong bases. So basically, if we add a bunch of hydroxide ion or a bunch of hydronium ion to a buffered solution, the change that would occur without the buffer is going to be larger than the change with the buffer. So basically, the buffer tempers the change that the addition of a strong acid or strong base would cause. Okay, and buffered solutions are going to typically consist of two things. They're going to consist of a weak acid and a salt, or a weak base and a salt. And it can't just be any salt. It has to be a salt that contains a conjugate ion. So in the example that we see here, we see acetic acid and we see sodium acetate. Notice that I have acetic acid and acetate, which is the conjugate base of the acetic acid. In the case of ammonia and ammonium chloride, notice the ammonium is the conjugate acid of the weak base NH3. Okay, so basically, guys, we have a acid or base and a salt that shares a common ion. Okay, so in this context, guys, we're going to have either acidic buffers or basic buffers, and so that's usually how we categorize them. And these solutions by themselves will have their own specific pHs, and we'll look at that. And if we add hydroxide or hydronium ions to this solution or these solutions, we will see a change in pH, but not as drastic as if we would have added them to a container full of water. So we're going to go ahead and look at the solution here of acetate ion and sodium acetate. So we have an equimolar mixture, basically meaning that we have the same amount of moles of the acetic acid and the acetate ion present. Okay, so if we look at this system, all right, the species that we're going to have present in solution that are going to be important for our buffering capacity are going to be our acetic acid and our acetate ion. Now, if I disturb this system, this buffered solution, if I disturb it by adding a strong acid. So in the context of adding, say, HCl, I know that I am adding H plus ion, okay, because the H plus ion is going to drastically affect our pH of solution. However, because of the fact that I have my conjugates present in solution, or my buffered solution, that's actually not going to be the case. What's going to happen is one of these species is going to interact with the H plus that I add. Okay, so which species is going to be able to behave as a base and interact with the H plus? The answer to that, of course, is the acetate ion. So what will happen is the acetate ion will react with H plus and produce CH3COOH, okay, so acetic acid. So basically the quantity of acetic acid is going to increase a little bit, and the quantity of the acetate ion is going to decrease. All right, so this will cause pH to decrease because the presence of more acetic acid means that I'm going to get more ionization of the acetic acid. However, the H plus ion, the hydronium ion all by itself, will not be present in that form, so pH will not decrease as drastically. Okay, in that same vein of thought, or that same thought process, if I were to add, say, sodium hydroxide, which we know is a strong base. Okay, so if I add sodium hydroxide, I'm adding hydroxide ion. So I have to think which species in my buffered solution is going to react with the hydroxide ion. And the answer to that, of course, is the acid. So if I add the strong base, the acid's going to come along and interact, right? And what we're going to produce is more acetate ion and water. Okay, so in this case, guys, we've produced more acetate ion. We've decreased the quantity of acetic acid. So the acetate ion will be present in a little bit larger quantity. All right, so if I decrease the amount of acetic acid, I'm going to subsequently increase my pH. Okay, and again, that increase in pH is going to be less drastic than if I just added hydroxide to a non-buffered situation. So now that we kind of understand how the buffering process works, let's go ahead and let's look at some math. So we have a buffered solution that has acetic acid and sodium acetate, and it's an equimolar mixture, okay, so 0.5 molar for each of the substances that are present. Okay, so of the substances that are present, we have our acetic acid. Of course, we're going to have sodium ion, and we will have an acetate ion. Okay, and H2O. Okay, so the species that we're going to be ignoring for this process, of course, are the sodium and the water. Okay, we're going to be paying attention to the acetic acid and the acetate ion. Okay, so since they gave us Ka for this solution, let's look at this from the perspective of a acid behavior. Okay, so we have our acetic acid, and we have our acetate. Okay, and we're going to have H plus here because we're, as I said, looking at it from the acid perspective. So we're going to go ahead and treat this problem as a simple ice problem, set up our ice table and our equilibrium expression. So now that we have our ice table set up and we have our equilibrium expression, let's go ahead and let's plug in the values that we know. So we know that we have 0.5 molar concentration for each of our species here of acetic acid and the acetate ion, and then of course no H plus. Okay, we indicate our changes like we have in the past, and then we get our values relative to X in our equilibrium positions. Okay, we're going to then take our equilibrium values and plug them into our Ka expression. Okay, so now that we have these values plugged into X, what we're going to go ahead and do is we're going to assume that the change in X here and here are very small. So we're going to simplify both the concentration of our acetate ion and the concentration of our acetic acid by dropping X. Of course, we'll need to check that for both of these, but we're going to go ahead and do that to simplify this process. We're also going to plug in our Ka value, which is 1.8 times 10 to the negative fifth. Okay, and so this is going to give us mathematically X being equal to 1.8 times 10 to the negative fifth. Okay, now I'm going to check that value versus the 0.5. And when we do that, we end up with a very small percentage of error, 3.6 times 10 to the negative third percent. Okay, so we fall within the confines of what's acceptable. Okay, so then we're going to go ahead and plug this into our pH calculation, which is going to give us 4.74 as our pH for our buffered solution. So we can simplify the process that we just did on the other slides by using something called the Henderson-hasselbalch equation. And so the Henderson-hasselbalch equation basically relates pH, pKa, and the log of the ratio between the concentration of our conjugate base and our acid. Okay, so we could have used this setup to calculate our pH of the buffer we've seen in the previous examples. And we'll do that here in a second. But what I need you guys to understand is that in the previous examples, we've had to check our X values when we drop them. So we've made the assumption, but we've done the check. In this context, obviously, we're not setting up an ice table, so the check isn't there. So you have to be careful with the values that you choose to use the Henderson-hasselbalch equation for. Now, a lot of times you can use it, especially when your Ka values are very, very small and your concentrations are relatively large. But if you start getting to where they're closer and closer to one another, you may want to make sure that you use the longer ice table approach. Okay, so the assumptions that we're making here then, guys, of course, is basically that the concentrations that we're plugging into here are basically the same as your initial values. And so those assumptions obviously are things that you need to be a little bit careful with. Again, it will work a lot of the times, but as you get a Ka value and a concentration value that are closer to one another, you may need to take a moment and do the ice table setup. All right, so guys, let's go ahead and let's use this really quickly and basically use the Henderson-hasselbalch equation to solve for the pH of our buffer solution. All right, so if we plug these values in, we end up with this equation here, okay, and If we go ahead and take the negative log of our Ka value, that gives us our pKa, okay, which is going to be 4.74, and the log of 1 is going to be 0. So the pH of our solution here is going to be 4.74, which is what we calculated when we used the ice table setup. Okay, so the Henderson-hasselbalch is basically a shortcut. Please make sure that you're plugging in the correct species in the relationship here, and memorize this equation. So now let's go ahead and look at the Henderson-hasselbalch application in the context where we don't have the exact same concentrations of our salts and weak acids or weak bases. Okay, so in this case, guys, we've been told that we want to know the pH of a solution with a 0.7 molar concentration of lactic acid and 0.25 molar concentration of sodium lactate. So in this case, guys, sodium lactate, the lactate ion is going to be our conjugate base, and of course the lactic acid is going to be our weak acid. Okay, so they've also given us Ka, so we're going to go ahead and plug all of this into the Henderson-hasselbalch. So if we go ahead and we plug all these in, like we see here, we have our concentration of our base, our conjugate base, and the concentration of our acid. We plug these into our calculator, we get 3.38 as our pH. Okay, so basically, straight up simple calculation. We could have, of course, plugged this into the ice table, but this is much easier. The next problem is a little bit different with respect to the Henderson-hasselbalch. Why? Because they're asking us to calculate the pH of what's going to end up being a basic buffered solution. So there's multiple ways we can approach this problem. I'm just going to continue to use the Henderson-hasselbalch in the form that we see here. So in order to actually do that, I need to make the information that I've been provided match up. Okay, so they provided me with a Kb, so I need to convert that to Ka, which is going to be 5.6 times 10 to the negative 10. And then we are going to go ahead and plug these values that we've been provided into the equation. So what I want you guys to notice here is that the way I've plugged in my base and my acid. Okay, so I know we've treated this above as conjugates, but in this context, understand that this substance is still going to behave as the base. This NH4 plus is still going to behave as the acid, so I'm going to plug in their concentrations in the base and acid positions respectively. Okay, so if we go ahead and plug this in our calculator, we end up with 9.05 as our pH. So as you can tell, Henderson-hasselbalch saves a lot of time and effort, so it's something that you may want to include in your practice. But make sure that, guys, that you can do both the ice table setup and the Henderson-hasselbalch. So now let's go ahead and talk about adding a strong acid or base to a buffered solution. We're going to use the same solution that we used in the last example. But in this situation, what we're going to do is we're going to add 0.010 moles of solid sodium hydroxide to this solution. And we're going to see how that sodium hydroxide affects said solution. Okay, so there's a couple steps that we have to do in order to calculate problems like that. First of all, we have to do the stoichiometry to determine the new quantities of each substance. We need to do an ice table setup and basic process to solve for x. Okay, so basically the new step that we're doing here is this stoich relationship, and we're going to look at that here. So in our previous slide, we talked about how we have a buffered solution that contains the acetic acid and the acetate ion, and that these are the species that are going to basically counterbalance any acid or base that's added. Okay, so when I add sodium hydroxide, I'm really adding hydroxide ion to the above situation. Now, we know that the hydroxide ion is going to interact with an acid. So in this case, the hydroxide ion is going to interact with our acetic acid. Okay, so when we go ahead and we represent what's physically happening initially when we add the hydroxide, we're going to show our acetic acid, we're going to show our hydroxide ion as both being on the reactant side, and then we're going to have our water and acetate ion as a product. Okay, so what we're going to do here is basically first figure out how the addition of hydroxide ion is going to affect the concentrations of our acetic acid and our acetate ion components of the buffer. Okay, so we're going to go ahead and look at the moles before of each of the substances. What we're going to do, guys, we're going to just assume that our solution for our buffer is a 1 liter solution. Go ahead and use that information to find out the moles of our acetate ion, or our acetic acid and our acetate ion respectively. Okay, so if we know we have a 0.50 molar solution, we take and multiply by 1 liter, we're going to know that we have 0.50 moles of each of those species. Okay, so since the molarity of our sodium acetate and acetic acid are the same, we're going to have the same molar amounts for both species. Okay, so we're going to have 0.50 moles of our acetic acid and 0.50 moles of our acetate ion. They've been nice, and they've also provided us with the number of moles of the hydroxide we've added. In this context, the sodium hydroxide has a 1-to-1 relationship with the hydroxide ion, so we have added 0.10 moles of the hydroxide ion. Okay, so now, guys, we have to figure out how the acid and the base are going to interact. They do so in a 1-to-1 fashion to produce one equivalent of the acetate ion. So what's going to happen is that the hydroxide and the acid are going to react and decrease in quantity and produce the acetate ion, which will increase in quantity. Okay, so what's going to happen here is that we're going to decrease our number of moles of our acetic acid. We're also going to decrease the number of moles of our hydroxide ion that we've added, and we're going to increase our number of moles of our acetate ion. Okay, and so what that is going to end up giving us is the following number of moles for each of the species that are present in solution. Okay, so we now have our quantity of moles of our acetate ion and our acetic acid after the hydroxide ion has been added. So notice what's happened is by adding this base, some of the acid has reacted with it. So basically we see a decrease in the quantity of that acid, and through that process we end up increasing the quantity of the acetate ion. Okay, so now we're going to use this information to go ahead and do step 2, which involves basically equilibrium approaches. So again, we're going to still be assuming that we have a 1 liter solution. So what we need to do with these values is we need to convert them back into molarity. Okay, so we're going to take our 0.49 moles per 1 liter and our 0.51 moles per 1 liter. Okay, and of course we're going to get our new molarities for each of the species. Now, obviously, if this was a different value, or if the sodium hydroxide was a solution instead of a solid, this would change, okay, this value of our volume. But since it's a solid that we added, there is no change there. Okay, so then what we're going to do here, guys, is we're going to go ahead and plug our values back into our equilibrium expression. All right, so we're going to set up our ice table here. We're going to set up our new initial concentrations of each of our species that we calculated earlier. Okay, so basically treating it now like a regular ice table problem. Okay, just like we have over and over again. Okay. And then we're going to plug this into our equilibrium expression and find our new H+ concentration and subsequently our pH. Okay, so now we plug this into our equilibrium expression. We're once again going to make the assumption that x is very small. Okay, and this is all going to be equal to 1.8 times 10 to the negative fifth. Okay, so we're going to do the math and go ahead and solve for x. And x is going to be equal to 1.7 times 10 to the negative fifth. Okay, so that's the concentration of my H+ ion. So pH is going to equal the negative log of our 1.7 times 10 to the negative fifth. Okay, and that's going to give us 4.76 as our new pH of this particular solution after the hydroxide has been added. Now recall the pH of the previous problem we did, or just the buffered solution by itself, was 4.74. Okay, so if we want to calculate the change in pH that has occurred after the addition of the hydroxide ion to the buffered solution, so what we're going to do is we're going to take our new pH of the solution after the buffer has done some work and subtract out the pH of the buffered solution alone, and that will give us the change in our pH value. So basically, the pH has increased by 0.02. Now guys, please understand that if we were to not have the buffered setup here, we would have a much more drastic change in pH. And if you guys go ahead and calculate the concentration of the sodium hydroxide added to a 1 liter solution of just water, and then subsequently calculate your pH, you'll notice that you get a much higher pH for that particular solution. So we know that the buffer solution basically tempers this change, and we see this here when we look at our pH difference. Let's talk about a little bit more detail of buffers. So basically we know that in equimolar solutions, like we've seen basically in a couple of our examples, we know that the pH is going to be equal to the pKa. And the reason why is because the log of 1, which would be the ratio that we would see in the Henderson-hasselbalch equation, is equal to 0. So equimolar solutions, we know that the pH is always going to equal the pKa. Okay, so the next thing we need to talk about is buffer capacity. So buffer capacity, guys, is the extent to which a buffer solution prevents pH changes. Okay, and buffer capacity is going to depend on several things. So pH is going to be the first one. So the closer the buffer pH is to the weak acid's pKa, the greater your buffer capacity is going to be. So the closer that buffer pH to the weak acid's pKa, basically the higher your buffer capacity. And of course, this is going to be facilitated by when we have a ratio between our conjugates that's going to be basically 1 to 1. Why? Because at that point, as we said before, the log of 1 is going to be equal to 0 and pH will equal pKa. Okay, so the second feature that's going to affect our buffer capacity is concentration. All right, so concentration makes physical sense. So if we increase the concentration of our acid and base pair, or our base and our acid pair, what that's going to cause is the ability to add more hydroxide or more H+ ion, and because there's actually physically more of these two species to counterbalance that change in pH. All right, so if we increase our concentrations of our buffer, that's going to make it where we just have more stuff in solution that's able to counterbalance the change. Okay, so these two features would be important in terms of determining, let's say, what acid is going to be a better buffer relative to a specific pH that we want to keep. So if we look at an example like this, so there's a specific pH of 4.30 that a chemist wants a buffered solution to have. And he's going to basically prepare that from one of these two acids and a salt containing the conjugate base. So in order to determine which one we would choose, the chloroacetic or the benzoic acid, we're going to utilize our knowledge about how buffer capacity is maximized. Okay, so we know that buffer capacity increases as the pH is closer to the pKa. So in this case, we've been given our Ka values. So let's go ahead and calculate our pKa's, which are going to be 2.87 and 4.2 respectively. Okay, so the buffer solution that we want to make is going to be the benzoic acid and its conjugates. Why? Because this pKa is closer to the pH that we desire. And of course, if we were trying to find what solution would potentially be a better, have a better buffering capacity, if we're comparing two equivalent solutions with respect to their pH, we would then look at the concentration values. And if we have more of our conjugate base and acid or conjugate acid and base pairing, there's going to be more buffer capacity in that specific solution.